Hello students, now in this video let's see operations on graphs. Operations on graphs. So in that one, first of all let's see subgraph. What is subgraph? Definition: let G and H be two graphs the graph H is called a subgraph of G if vertex set of H is a subset of vertex set of G and edge set of H is a subset of edge set of G. If H is a subgraph of G, then first all the vertices of H are in G. All the vertices of H are in G. Second, all the edges of H are in G. And third, edge set of H has the same endpoints, or each edge of H has same endpoints in H as G. For example, now let me take a graph as, suppose this is a graph. With vertices, suppose A, B, C, D, E, F. Okay, here also G. Fine. Now this is graph G, suppose. Now suppose here let me take here, this is H1 and this is H2. Okay, now here you can observe the same graph will occur here. Look at this. But what about this? Is there any edge between C and E? Here no edge between C and E. And there is an edge between D and F. here that age is absent. So here we can say H1 is a subgraph. H1 is a subgraph of G, but H2 is not a subgraph of G because age joining C and E is in H2 but not in what? G. This is the reason behind that. This is the definition of subgraph, and these are the important conditions to become the graph will be subgraph of the original graph. Now next thing we have to see a spanning subgraph. Definition: let G and H be two graphs a spanning subgraph H is a subgraph containing all the vertices of G. That is, vertex set of H is subset of vertex set of G, and age set of H is subset of age set of G. Then H is a proper subgraph of G, and if vertex set of H is exactly equal to vertex set of G, then H is a spanning subgraph of G. Note, spanning subgraph need not be or need not contain all the ages of G, but it must contain all vertices of G. Vertex sets are what? Equal. While in proper subgraph, these are what? Subsets of that original graph. Okay. For example, now suppose this is a graph. Let's take this. Suppose A, B, C, D, and let it be E. Okay, let it be G. Now here, let me take this is suppose H1. H2, and suppose H3. Now these are the subgraphs of this, but which are the spanning subgraphs? Look at this. H1 has all vertices here, 5 vertices, so 5 vertices are here also, 5 vertices are here also, but here only 4 vertices. So H1, H2 are what? A spanning subgraphs, while H3 is not a spanning subgraph. The graphs H1 and H2 are spanning subgraphs of G, but H3 is not a spanning subgraph. Of G. Next, edge disjoint subgraphs. Edge disjoint subgraphs. Two or more subgraphs G1 and G2 are said to be edge disjoint subgraphs. Edge disjoint subgraphs if edge set of G1 intersection edge set of G2 is an empty set. Again, vertex disjoint subgraphs. So, two or more subgraphs G1 and G2 are said to be vertex disjoint subgraphs if vertex set of G1 intersection vertex set of G2 is what? An empty set. Now here note that vertex disjoint set or vertex disjoint subgraph is always an edge disjoint subgraph. If vertex is not common there, so edges wouldn't common there because edges are incident on those vertices. Edge disjoint subgraph. But the converse of this one is not true, means the edge disjoint subgraph need not be vertex disjoint subgraph. If we eliminate an edge, it doesn't mean that we have eliminated a vertex. Vertex may be there, so that time the intersection wouldn't be an empty set. That's why the converse is not true. Let's take an example here. Let the graph suppose let it be V1, V2, V3, V4, V5 with edges E1, E2, E3, E4, E5 and E6 suppose. Now this is G suppose. Now two of them let's take. Here let it be V1, V2, V3 and here let's take now V1, V2, V3. So here E1, E2, E3, okay. Here V2, V4 and V5. So here E4 and E6. So now look at here, the edges are E1, E2, E3 while the edges are E4, E6. So edges are disjoint, right? Their intersection will be an empty set. But what about vertex set? It is V1, V2, V3 while here V2, V4, V5. So V2 is common in between them. So vertex are not vertex set are not disjoint, right? So edge disjoint are these, but not necessary they are vertex disjoint. Let it be G1 and this will be G2. So here E of G1 intersection E of G2 is an empty set implies edge disjoint. Edge disjoint, right? But vertex set of G1 intersection vertex set of G2 is not equal to what? Phi. So it implies not vertex disjoint. Is it okay? Right? So every vertex disjoint subgraph is an edge disjoint, but edge disjoint need not be vertex disjoint. Fine. Now the next part, next thing we have to learn about deletion. So here in a graph, deletion are of two types. Deletion means a removal, right? So these are of two types. So one thing, vertex deletion, and other is edge deletion. Vertex deletion and edge deletion. Okay. So what is vertex deletion? It is vertex removal. If G is a graph and V is in vertex set of G, then G minus V is deletion of vertex from a graph G. That is same as subgraph of a graph G obtained by removing a vertex V from G. Vertex V from G. Or note that removal of vertex implies removal of edges which are incident on that vertex, Now another part is what? Edge deletion. If G is a graph and E is an edge set of G, then G minus E is deletion of an edge from a graph G. Okay, that is subgraph of a graph G obtained by removing an edge E from G. Again, here also we can note removal of an edge. Here it doesn't imply the removal of its end vertices. Now let's see example on this. Suppose V1, V2, V3, V4, V5, V6. Here E1, E2, E3, E4, E5, E6 and E7. These things. Let it be G. Now suppose we have to find, or let's see, let we found G minus V4. Suppose G minus V4 is what it be? We have to delete this vertex. So after deleting this vertex, these edges are also get deleted. So simply V1, V2, V3, here V5 and V6 we have to write. So edges between these vertices we have to write simply. So removal of an vertex implies removal of an edges incident on that one. So here only V1, V2, V3, this is V5, V6 and the edges E1, E2, E2 is here. Here this is E3, E4 and what? E7. Two edges are get deleted. And let we find G minus E4. What it is? G minus E4. So simply this E4 we have to omit. So deletion of an edge, but here we cannot delete the vertices. We have to keep these vertices as it is. Simply that edge we won't draw. Fine. There V1, V2, V3, V4, V5 and V6. Here E1, E2, E3, E5, E6 and what? E7. As such, the deletion can occur. Next thing, let's see the definition. Vertex induced subgraph. Let G is a graph with vertex set V and edge set E be a graph, and suppose W is V1, V2 and so on up to Vi, sum of the vertices from subset of whom? V. Okay. A subgraph of G whose vertex set is W and edge set consists of those edges. Edge set consists of those edges in G which has both end vertices, in W. Means whatever edges are there in G, and if W, whatever number of vertices in W and edges of G which are incident on those vertices, then all of these edges should be present in that graph. Such a subgraph is known as what? A vertex induced subgraph. Both end vertices in W is called a vertex induced subgraph. Another is what? Edge induced subgraph. Let G is be a graph and suppose F consisting sum of the edges here, EJ suppose, is a subset of edge set of graph G. A subgraph of G whose edge set is F. Edge set is F and vertex set consists of those vertices in G which are end vertices, of edges of F. of edges in F is called a edge-induced subgraph. Means simply a graph obtained by collecting few of the vertices or few of the edges. If few vertices we have been taken as a new subset of the original vertex set, then all edges on those vertices, incident on those vertices, will give us a subgraph. That type of subgraph is known as a vertex induced subgraph. And if we have been taken an edges, then all those edges are incident on those vertices. That graph with those edges is known as edge induced subgraph. Fine. Now next thing we have to see the complement of a graph, self complementary graph, union, intersection, ring sum, and product, as well as a fusion of vertices. So these parts we will see in next video. Thank you.